transport.
So let me begin by thanking my good friends Urna and Anupam, and also acknowledging that under rather stressful conditions, they're sort of bravely soldiering on and carrying out this meeting. And so I'm here because also, so at the outset, let me sort of apologize that I'm not really, my work really doesn't fall into the main theme of this meeting, hence I'll sort of try to connect at least some of these words to what I'm going to talk about. It's all right if I don't finish, and this is largely aimed at the students. What I want to stress is the theory and the applications part of this conference. So what I'm going to discuss in the beginning is the general theoretical framework in which people like me work on in turbulent transport problems. And then if we have some time, we will discuss a little bit about some problems which may fit in, especially with the previous speakers' talk. And I should, again, just for context, sort of remind you that some of the phenomena that you are going to see in the next few slides will remind you a lot about the motility-induced phase separation problems that were being discussed in the afternoon. But what I'll try to tell you a little bit about is that the physics is going to be vastly different. So in case there are no other take-home messages from this talk, what I would like you all to remember is what sort of physical problems that I'm going to talk about. And of course, I'm making a broad claim by saying that in the next few slides we'll discuss equations which are universal enough to cover all these types of problems, and I'll sort of give you relevant caveats. What you do see here, and these are sort of generic examples of turbulent transport problems, are problems where there are particles, which could be at the scale of astrophysics, geophysics, volcanic eruptions, atmospheric sciences. The microphysics of cloud formation is a particularly sort of catchy example in our field. But all of this somehow involve particles which are small, and we'll come to how small they are, and in each physical system the smallness varies, which are immersed in a flow which is turbulent. All right, so these are the general sort of kinds of problem for which I'm going to set up the theoretical framework. So where do we begin? So a simpler question, because all those sort of movies were quite fanciful. So a simpler question that one could begin by asking is, what is the effect of a carrier flow on the motion of a single particle? All right, so for that we need to worry about both the carrier flow and the particles, and we'll try and slowly set up the equations of motion governing them. For the fluid, we need, so I sort of, beg your indulgence if I'm being too pedantic or too slow here, but for the fluid, and that's why I said it's mainly aimed at students who are not working in turbulence and fluid mechanics. For the fluid, the ingredients are really viscosity, which is important at small scales, which will separate the flow of honey from air. Then there is the issue of energy injection, which is how do you stir up the flow? Okay, typically here you see an example of a grid, what's known as an active grid in a wind tunnel through which you pump in air. And lastly, you have to worry about boundaries. So this is a sort of visualization of the flow past a golf ball and the flow past a baseball, I think. And if you look closely enough, the sort of vortex shedding behind, because of the structure of these balls, the ridges, etc., are going to be rather different. So these three are critical ingredients in trying to set up the equations of motion or understand the physics of the carrier flow. But we still need to write down equations, of course. So the mathematical framework with which all of us deal with is essentially what is the velocity, fluid velocity u at position x and time t. It wouldn't surprise any of you that our starting point is the Navier-Stokes equation. I impose incompressibility because of the problems that I'm going to discuss are for flows which are incompressible. And sort of this has a long history, which I will not go through, but the sort of the founding heroes of this field go back to Leonard Euler, Navier, and then Stokes, the British mathematician, a few decades later. So for turbulent flows, since I'm mainly going to focus on particles, let me sort of give you a working definition of what I would mean by a turbulent flow. And as a theorist or a numerical experimentalist, what I'm going to end up doing often is to solve this equation and obtain the velocity field as a function of space and time. All right. So for turbulent flows, a working definition would be the solution of this equation when the viscosity is going to be very small. All right. And generally, these flows are a very good example of what one would in the class of non-equilibrium statistical physics. And the telltale signatures of these flows are the fact that they're chaotic, they're irreversible, they're intermittent, and most crucially, and we'll sort of come back to this in a bit, they have multiple length and time scales in the problem. This is very different from laminar flow, where you do not have these features. All right, so essentially solutions of this equation, if you're able to solve it on a computer, and you take a small enough coefficient of viscosity nu there, you'd end up with solutions. This is in 2D, which looks like this. This is the vorticity field, but which has these sort of signatures. All right, so that's going to be my fluid. Now, what happens to the particle, which is going to be immersed in a fluid velocity field, which is a solution of this guy? So to understand the equations of motion of this particle, the sort of simplest starting point is to take a spherical particle of radius a, and the other parameters of this particle are defined there, and then essentially write down Newton's laws. So essentially what we are going to do is try to understand what is the force of the particle. The easy one is, of course, the force due to gravity. That's just mpg. And then the hard one is to try and integrate all the stresses coming from the fact that it is immersed in a fluid. So there's a fluid hitting the walls of this particle, as it were, and then to try and sort of find out what this term really is. So luckily, this was a solved problem. It actually goes back, the history of this, again, is quite long, and you can see it from the years. This goes all the way to Bassett's original work in 1888. But our starting point is the work of Maxey and Riley, who sort of integrated this surface integral on the surface of this sphere and found out that this is a horrendously bad-looking equation, all right, for want of a better word.
We ignore the back reaction?
Yes. So far I'm just talking about the fluid affecting the particle. Back reaction I'll probably speak at the end of this talk. Most of the talk I'm ignoring back reaction, and you'll see why that's a good assumption to do for the problems we are looking at. So again, this is just in case any of you are sort of working on something similar. So the various terms which form this equation, some of them are well known. For example, the buoyancy term we all know from high school. Then there is the force due to the undisturbed flow. Then you have the Stokesian drag. Again, that is something that we are familiar with in many problems. Then there is added mass, which is a very strange sort of force that people in fluid mechanics know much more than elsewhere. And then there's the Bassett history term. So what one does, or people like me do, is essentially to simplify this equation. How? So from here, I come to this equation, which looks less formidable, by assuming that my particle is small. All right? So all the sort of a squared grad squared u, a is the radius of the particle, if you remember, drops out of the equation by assuming that they're small enough. I should also point out, as an advertisement to the work of some of my colleagues here, Ganga, etc., sort of in a recent paper evaluated this term very carefully. But we drop this out, and then we further assume for the rest of this talk that we are going to deal with heavy particles. By heavy, I mean the density of the particle is larger than that of the carrier fluid. So if you want a mental image, think about a water droplet in a cloud. All right, so there's a turbulent flow and you have a water droplet. All right, so again, depending on your sort of training, you might want to think about this equation with all the parameters stuck in, or you can just think about the equation for the particle as a slip velocity in the carrier fluid and a drag timescale associated with this. So these are the working equations that people in turbulent transport, or people from my background in turbulent transport, like to look at, which is a non-engineering approach, where you look at a carrier flow, which comes from a solution of the Navier-Stokes, you pick u, you stick it in the equation of motion for the particles, and then you can sort of look at the dynamics of these particles. And there are, we'll come to these probably in a bit, there are sort of non-dimensional parameters associated with this. Yes. There's no back reaction yet. Yeah. Oh, the big equation? This comes from just calculating the sigma, the stress tensor on the surface of the particle. And this was worked out by Max Rayleigh. It's a complicated derivation, so I won't even attempt to give you a sort of flavor to it. But some of these terms, you can sort of see it more. I mean, from here, you can actually, if you remember how you calculated terminal velocity of a ball falling in still liquid, now you put a velocity there, and you'll see this term will come out of the 6 pi eta. Sorry? The history term is, as the particle moves, it creates a little disturbance. What is the effect of that as it accumulates? All right? That's right. And that has a very devilishly looking singularity sitting in the denominator. You had a question? Yes. Yeah. Here. So the particle is in this flow. So in the dynamics of the particle, the fluid velocity. So think about a water droplet in air. As it moves, why does it move? Because the air is moving around it. That could be one reason why it moves. So it's sort of the fluid velocity at the position where the particle is affects the dynamics of the particle, right? So it goes in there.
So the F, of course, is important in the driven of Stokes equation, right?
This one?
Yes.
It's a forcing term which sort of keeps it in a non-equilibrium stationary state.
Would that also appear in this friction 1 over tau p?
No. This F just sets the statistics of U, which appear, so not in a direct way.
In the friction.
Not in the friction. Not in the friction. Right? So friction would just be the Einstein, the 6 pi eta term, which is
probably not correct, right?
That's not correct, but for low enough speeds, that's reasonably correct. You don't need the nonlinear correction to the drag. Okay, this is very nice because all these three questions sort of are encapsulated here. Are these approximations valid? Since this is not a specific audience, so let me show by pictures whether they're valid or not. So the one that I'll do, and that's partly because I was involved in this work, is some years ago we did experiments in Eberhard Bodenschad's lab in Göttingen, where we looked at small water droplets in a turbulent air. It was really a big football where you played Metallica and got the air inside the football turbulent, and then you injected small droplets in that turbulent flow, and you sort of traced the trajectory of this. Having traced the trajectory of this, you can, for example, calculate many things. One of the easy things that you can calculate is the PDF of the relative velocity between two droplets conditioned on their separation, right? And what we did was we also solved this equations on our computer and calculated the same thing. Remember, I threw out so many terms. The good thing was, and I'm just showing, and this is just to sort of convince you that these approximations are all right, is to actually plot the PDF of both these guys from the simulations of these simplified equations and from the experiment. And you see that the symbols are from the experimental data, the lines are from our simulations. You see that, except the tail, of course, that the agreement between the experiments and these simplified models is not too bad. There are issues here which I won't go into in this talk. Why there is a disagreement, for example, on the right tail much more than on the left tail and things of that sort. But what I wanted to emphasize with this is not to hide the fact that there are discrepancies, but just to show you that this simplified model isn't a bad approximation to actually study the motion of a single droplet or multiple droplets in a turbulent flow, all right? And we were also able to reconstruct trajectories which seem to do a good job. Very good. So the question really then, would come to mind is, what makes such particle-laden flows interesting, okay? So one of the central features of these turbulent, this sort of system of particles in a turbulent flow is this issue of preferential concentration. And here is what I mean when I said this has a natural connection to the motility-induced phase separation talks that you had in the afternoon. So you begin with a homogeneous distribution of particles. So the white are the particles. And then as they evolve, so I'll just focus on this because it's a 2D slice and hence easier to see. As they evolve, you see that these chaps tend to preferentially concentrate. They are no longer space filling, okay? And this sort of makes this whole business of turbulent transfer and has consequences which we are going to discuss. And the preferential concentration that you see, so the divergence of the particle velocity field is proportional to 1 over Stokes. Stokes is that friction that you were talking about, tau p, suitably non-dimensionalized with some fluid time scale, right? So what is the consequence of this? So first, let us sort of summarize what we mean by preferential concentration. Here again are snapshots of particle fields, and you see the same behavior, which is you have clustering of particles. So there are empty spaces, and then there are regions where particles concentrate thickly. So essentially, this is due to the fact that you have dissipative dynamics for particles with inertia, as a result of which the phase space of the particles shrinks, and hence in real space that's projected into this behavior. And so one of the ways that, I'm just looking at the time, so one of the ways that people actually quantify how clustered you are, and in other fields you can think about pair correlation functions, etc. But for historical reasons, one of the way people in our community quantify this is to ask the question, what is the probability of finding 2 particles within a distance r, right? If particles were homogeneously distributed in 3-dimensional space, for example, then the probability would scale as r cube. You're sitting on 1 particle, construct a sphere of radius r. In that volume, you'll have number of particles proportional to r cube. But of course, these are not homogeneously distributed, and hence what you have is this guy scales with r as a power d2, which is not equal to the spatial dimension. And in this sort of rather seminal paper by Jeremy and others in 2007, they actually calculated this D2. These again are snapshots of this preference. So the reason I have so many photographs, pictures of this is, in case there's nothing else that you take back from this talk, I'd like you to remember the fact that particles tend to segregate in turbulent flows. So Jeremy...
The interaction of the particles is not important.
This is non-interacting. It's what's known as, yeah.
Hardcore.
No. So we'll come a little later to problems of crystal formation, etc. If we have time, sorry, or we can discuss this after the talk. So what they calculated was D2 as a function of the Stokes number, which is the particle relaxation time suitably non-dimensionalized. And it doesn't surprise you when this is 0, that is that tau p in that equation is 0, so the particles are like tracers, blob of ink in water, then D2 is 3, because tracers uniformly sample the fluid goes everywhere, the tracer goes everywhere, so D2 is 3. When the particles are very large or they have a lot of inertia, they again don't care about the fluid, right? Because they don't see the fluid. And again, they bounce off and sample the whole of phase space, and you again end up with D2 being equal to 3 in the large Stokes limit. The interesting thing happens at intermediate Stokes number. What you have are these fractal clustering, and hence this, by the way, this is in the community, we call this the correlation dimension. This has a certain minima, all right? And so you have, and that corresponds to this shrinking of the particles tending to agglomerate. So again, the question that one sort of, and I was conscious of this while preparing this talk because I know I'm not sort of speaking to my own community, is to keep on asking the question, why bother? Prashant, you have the answer to the question, or you have a question? Yeah.
So, like, the density is not homogeneous, right?
Yeah.
It should depend on which R I am computing.
No, yeah, but this is for R which are smaller than some length scale in the fluid. So if you calculate here, eventually you'll have an R to the D2. There's a power law range, which will be just this. As R becomes large, so for example, if you're sitting here, and R is very large and you hit a void there, sure, this is true, but this is for small enough R. So, okay, good. So why bother? So one of the reasons why we bother is the fact that particle-laden flows are ubiquitous. I mean, that was the point of that second slide, which has some very fancy movies, all right? And understanding this phenomena is crucial to a lot of things. One of the questions where this really impacts, and this is best sort of advertised through this editorial in Science a few years ago, it's a bit dated now actually, 10 years ago, is the fact can we understand the formation of clouds without understanding turbulent transport? And I'll summarize that in a line, is the following. Suppose you started with small nuclei in the cloud and you waited for them to grow big enough for them to precipitate and rain happen. A way to do that would be to think about coalescence or condensation, which would lead to the growth of these droplets. If you actually work out the condensation rate, given that there is saturated water vapor, you'd see that it will take it will take a time which is orders of magnitude longer than what you see for a cloud to form and rain to come down. This is especially true in tropics, of course. So what's going on? So the other way in which droplets can grow is through coalescence. All right? For particles to coalesce, they have to interact. They have to physically come in contact with each other and coalesce. If you look at the typical mass loadings of a cloud, they're intensely dilute. So if all these nuclei droplets were homogeneously distributed, the chance of them hitting each other would be very small. And so coalescence and hence growth of droplets and hence rain would not, really happen. So what we started realizing in the last few years is that the fact that there is this notion of preferential concentration underlying the dynamics of such particles ensures that even in dilute suspension, there are pockets where a lot of these particles come close to each other, and hence the rate of collisions or coalescence can actually increase, something you can't predict without actually understanding this process by which particles get close to each other. All right? So this is one of the sort of answers to why and what should we understand. But this sort of still begs the question, how do I start thinking about answering such questions, right? Yes, sure.
You started your reasoning from the dissipative character and the phase space contraction.
Right.
But that's in phase space, meaning that it can also be
XV.
that the velocity goes to zero,
Absolutely.
basically, or equal to u, which is a very strong phase space contraction, but in configuration space, it can still spread.
Yes, but what we know is, and I haven't gone through that, is that essentially, let me do it on the blackboard. Essentially, if you are in d-dimensional space, the physical space in which you are, then d2 in the sort of tau p going to zero limit, and this you can show using the standard tools of NLD, this goes to d. In the other limit, and I think that's the one you have in mind, this actually goes all the way to 2D, if you're thinking of the XV phase space. The projection of this on the configuration space, and this one can show systematically, ends up as just T. And this you sort of, well known through theory and experiments. Right. Thank you. When I mentioned phase space, I should have pointed this out. Okay. So essentially, what I'm going to sort of build up is that understanding, this word understanding really means that we ask simpler questions of how aggregates merge, collide, or settle, and preferential concentration sort of plays a critical role in this. So I'm going to sort of tell you a little bit about the typical questions because, in the spirit of this meeting, I would actually like to go to interacting particles, but I think it's interesting sort of to see this. At least it might encourage you to pick up some papers on this area. So one of the questions that people ask is, how fast do droplets settle under gravity? And what is the role that this whole, the dynamics governed by these linear Stokes-Drags model actually gives you? So what I'm going to show you a little bit, and not the details, and we can discuss this. So this is from a paper a few years ago by some of us, is the fact that if you actually look at the settling velocity of a droplet in still air or in turbulence, and you actually see, is there an enhancement in settling? So essentially, you can calculate the actual settling velocity under gravity that you measure and subtract the typical velocity it would have if there were no turbulent flow around it. What you end up seeing is that because of turbulence, there is an and this is plotted versus the Stokes number, there is an enhancement of this guy at intermediate Stokes number, okay? And that leads to several consequences on how droplets precipitate in a cloud. And there are features as to how, as to the shape of this curve, etc., which we think we understand very well now. Another typical question would be, how fast do droplets collide? And this is where interactions start becoming important, because if they really collide or impact each other with large velocities, then if you're trying to build up collision or coalescence kernels a la Smoluchowski, then you need to factor in fragmentation and other aspects of this problem. And so this is again a question that people have dealt with, which is when you have two droplets which are coming close to each other, are they colliding with very large velocities or with zero velocities if they're mimicking the flow very closely, because two fluid particles adjacent to each other will have vanishingly small velocity differences, right? But if the particles have inertia, they decouple from the flow. And in principle, two particles from far away with uncorrelated velocities can hit each other with arbitrarily large velocity differences. And then finally, you can ask questions about how fast do droplets coalesce. So you can begin with a monomer distribution of, so these simulations, for example, had over 1 billion particles in a really large sort of turbulent setting. And you can ask, I begin with 1 billion particles of size 1 micron, let's say. How long do I have to wait to get a sizable fraction of 50 micron particles? And if it's 50 microns, then they start to precipitate, right? And then you can sort of use Smoluchowski-like equations, you modify the collision kernels there and try to understand what is the role of turbulence in actually accelerating the process of coalescence. So just to recap this part of my talk, and I'm sort of halfway there, is to say that in the last 10, 15 years, there's been tremendous progress in understanding the dynamics of small spherical particles in turbulent flows, all right? By small, I mean smaller than the characteristic length scale of the fluid, which is known as the Kolmogorov length scale, but let's not worry about that level of detail. And what we now understand are the basic principles and the consequences of the dynamics of such small particles in a flow field in an environment which is harsh, hostile, chaotic, random, like turbulence. Okay. Having understood this, there's a question which automatically emerges, is the following. What about internal structure, or when you have other degrees of freedom in the problem, right? Because these were spherical particles which have less internal degrees of freedom, but you can sort of try to ask the question about what happens when you have an internal structure or another degree of freedom in the particles which are in a turbulent flow. So one of them could be, for example, if you want to study the deformation of a large droplet. So you begin with a large droplet, which is not small. It is in a flow which is turbulent. It shears, it deforms, it stretches, and the droplet breaks up. So you could ask questions of that sort. Or you can sort of talk about, and I'll talk a little bit about this object in this seminar. Or you can ask questions about what happens when you have polymers, chains, and macromolecules. So stuff which have internal degrees of freedom. It could be small spheres connected by Hooksian springs, or it could be polymers, for example, which have very well-known rules of interaction. By the way, I should tell you that shamelessly, I'm just sort of plugging things that we've been working in our group when I talk about more degrees of freedom and interactions, all right? So this is a completely biased representation. Or you can sort of discuss spheroids and ellipsoids. This problem becomes rather important when you go from warm clouds to colder clouds, the cirrus cloud, for example, where you have ice crystals whose shape are certainly not spherical and which have immense importance, for example, nowadays in global warming, because the orientation of these ice crystals have an influence on the global heat budget. And so, so let me just flash. Pratik is a student at JNC. With him, we've been looking at a lot about the orientation of such objects and ice crystals, cirrus clouds, etc. And finally, you can put in interactions, Lennard-Jones, hard sphere, what you will, and you can see that even in a turbulent flow, you can actually construct crystalline aggregates which sort of seem to have some importance in astrophysical settings. So these are sort of, to my taste, some of the systems where one cannot avoid going beyond the spherical particle limit. So I'm going to discuss a little bit in the next half an hour of two of these classes of problems. One certainly, and two if I have time. So the first problem has to do with this object. So what is this? So this is the simplest extended object that one can think of. It's a chain of point-like traces. So each of these circles are tracer beads. So tau p is exactly 0. And we'll insert tau p non-zero in a while, which are connected through elastic couplings with its nearest neighbors. So in principle, this chain can stretch. All right? And what we are going to do is to put this object into a turbulent flow and try and see what's going on. So one of the caveats that I would like to sort of underline straight away is that this is a toy model, and this is far from a real fiber. It's getting there, but it's still far from a real fiber, partly because these links are phantom. There's no mass associated with the links which couple these beads. And to this audience, I don't need to convince that use of such elastic chains has a long history in statistical physics. Embarrassingly, in turbulence, this is a relatively newer sort of subject, and it's only in the last few years that, last couple of years really, that people have been looking at chains and fibers in turbulent flows from a variety of points of view, be it buckling, be it trying to use them as two-point probes to understand the physics of turbulence, etc. So the question that we asked was, what is the effect of elasticity in determining the dynamics in a turbulent flow? Before I give you the answer, just to remind ourselves, if you just had tracers, which are really the beads making up this chain, they would fill up the phase space uniformly. There wouldn't be preferential sampling. So now I take a bunch of these tracers, 10 of them, for example, and connect them all with springs. So this question was sort of, answered. Jason, who was a postdoc, now a faculty at IIT Bombay, Noelita is at Los Alamos, and my collaborator Dario Vincenzi in Nice, and it's already a bit dated. Okay, so the simplest description of the elastic chain, what we do is we generalize the Roos model for a sequence of identical beads with elastic links. All right, and then what one can do, so I'm going to show you for a dumbbell, which is just two beads and a spring. And we can write down the equations of motion for the link, capital R, the center of mass, small r. And essentially, they depend on the fluid velocity field at the position of the beads, the elastic coupling, which gives rise, if you look at this tau e term, which gives rise to a new time scale in the problem, the elastic time scale, which will lead to a certain Weisenberg number. It's very similar to the Weisenberg number if you know about polymers in flows. And one can sort of write, and then one can generalize this to n beads. All right? And at a technical level, what we work with are what are known as Fenny links. So they have a finite extension. And that finite extension is set by this quadratic term. It sets the maximum length that the link can have.
And what is psi?
Psi is a noise, is a white noise, a thermal noise.
Gaussian.
It's just a Gaussian white noise, uncorrelated. It actually really doesn't play much of a role except to set the equilibrium length. I mean, it really doesn't affect the dynamics as much. This we had checked. Okay, so what happens is the following. So so if you look at the time evolution of these chains, they start out very small, they're elastic, and then they stretch. So you see that these chains are getting longer, and then something rather crazy happens. When they encounter a vortex, as they would along their dynamics, they get pinned. And they get stuck in these vortices for a very long time. All right? So although my chains are massless and tracers, they show this rather strange preferential sampling of the vortices in the flow. So essentially, when a chain encounters a vortex, it starts coiling up, and it can never, well, never is a strong word, but it does not leave the vortex for a very, very long time, right? And there's a snapshot which actually shows you, in some sense, the process in which these chains tend to coil up in these vortices. And then, Jason, Noidita, and Daria, they were, with them, we were able to quantify this effect rather nicely in terms of measuring what is known as an Okubo-Weiss parameter, which is, forget the definition, but which is a point-by-point measurement. So in a turbulent flow, I can have values of lambda everywhere that I want. Lambda positive means that the point there is vertical, there's a rotation, and lambda negative means that it's a straining and there's stretching in the region. So what's curious is that you need these straining regions for these chains to stretch out, and then they get trapped in these vortices, right? And so one is able to make measurements of the PDF of these lambdas along the center of mass of these chains to actually quantify very nicely what we visually see there, all right? So one of the questions that you can ask is, how universal is this phenomenon? So a way to ask is the following. So again, for a while, I will just ask you not to ignore the slides, but just look at me. So suppose I make a chain, which is this pen. I can make it by having many beads connected by small springs, or I can just make this pencil with 3 beads, 1, 2, and 3. Does it matter? All right? So what we showed was that if we were to define a parameter where LF is the typical length of the fluid field or the vortex scale, so LF would be this length scale, the circle, let's say the diameter of this roughly circular vortex. N is the number of beads that I have in the problem, and the length of that pen that I was showing as U is LM. Then for a chain which has more beads and smaller segments connecting these beads, and this is mean lambda, you will find that as a function of Weisenberg number, if phi is large, which is, I'm just trying to sort of reinterpret this number here, if phi is large, so if you have more number of beads, then you preferentially sample the vortices and then you stop doing it. However, if this number is small, then you tend to saturate to a positive value. Irrespective of your Weisenberg number, which is the degree of elasticity, you will always sample the vortices. You need a sort of critical Weisenberg number, or critical elasticity for them to stretch to be long enough, where you do it. So the interpretation of this is just the following. If the links connecting 2 beads, so here are my 2 beads, if the link connecting these 2 beads are larger than the length scale of the vortex, then I can have a situation where 1 bead is inside the vortex, the other bead is outside the vortex, and whatever I do, I can never fold it back and trap it in the vortex. So I need the sort of typical interbead separations to be at least small enough to be of the vortex length. So then one bead gets trapped, the other bead is also in the vortex, and then you have this coiling mechanism which takes over, which gives rise to this rather dramatic effect. And this is sort of shown very nicely in this sort of simulation of dumbbells, where you have just 2 beads. They're ramrod straight, as they should be, but they'll never get trapped because the separation between 2 beads is much larger than the vortex, so that they never coil back, right? So I'm, of course, sort of skipping many of the things, but you can sort of take a look at this for more details. So again, the question of universality comes in. Is it true in 3D turbulence? And I should end soon. The short answer to that question is yes, but it's a qualified answer. So this is a recent paper, and Rahul Singh, the grad student who worked on this, is sitting right there, which will appear in Filtrans soon. What you see is that, like the 2D picture, in 3D you see a similar preferential sampling. I say it's a qualified answer because the vortices in 3D are actually elongated structures like this, so you also have a stretching along the vortex direction. And that makes the interpretation from 2 to 3 much more subtle than what it is. The other question, of course, is what happens when you put inertia on the beads. So these are 2D simulations, again by Rahul, which, I mean, these are more funny things. So why is this important? So let me just address that. We talked about elasticity, right? Now, if you have these beads which have masses, then purely mechanically, the beads would never like to be in a vortex. They would be centrifuged out. Elasticity would like them to be in the vortex. So there's a competition between the inertia of the beads, which wants to get out of the vortex, and the elasticity, which wants to coil it inside a vortex. So what we wanted to see, again, this is sort of at the proofreading stage in PhysRev E, what we wanted to see, what was the competition between these two competing effects. What is rather interesting, and we really don't have a way to understand this except to say they look very nice, is these chains which have one bead which is inertial connected by an elastic filamentary tail. It sort of feels it should mimic something biological, but we have no idea. You see something rather nice. The tail gets pinned to the vortex. The poor head circles around it like a Ferris wheel, and this goes on forever. So the tail, because of elasticity, gets pinned to the vortex. The head bead has mass. It doesn't want to come inside the vortex, and it goes round and round in circles. Modeling spiders, etc. I don't know. It looks nice, all right? Okay, so the sort of take-home message is that these features are presumably rather universal, and this is a rather sort of novel mechanism by which we can understand interacting extended objects in a non-equilibrium fluctuating flow such as turbulence. I got most of the words in the conference title in that sentence. So what we are doing now is, so what's the conclusion of this section? Is the fact that there is a rather interesting preferential sampling of flows via these elastic interactions which lead to phase separations of where particles are, and there's a nice competition between inertia and elasticity. So right now, Rahul is looking at these sort of problems which have to do, well, the interesting problem is this: what happens when you have rigidity or there's a cost between stretching? So you put a little cost in, you think about hinges between, for a given bead, the two links that go out, there's a bending potential. How does that play a role? All right, in 3D, we have some evidence for this. And Rahul is setting up some nice active filaments, and also, I'm told, he's looking at breakup statistics of these objects. So I have 17 minutes. I will not take 17 minutes because it's been a long day. But let me sort of end by something fun that one can do, because I had that biology slide. So with a couple of summer students, we also had fun by sort of studying these objects in a turbulent flow and trying to understand how to sort of apply collective motion of microorganisms in a turbulent environment. Firstly, and let me stress this is not active turbulence that I'm going to talk about. It's not bacterial turbulence. My organisms are not stirring up the flow and then making it look turbulent or look chaotic. I'm going to talk about what happens, for example, to some classes of zooplankton, which are already in a turbulent medium, and the medium would be turbulent irrespective of whether they were there or not. And what we are going to try and ask is whether this sort of behavior happens. The reason why this question is interesting is because of turbulent mixing, it's not clear whether any collective dynamics can arise because of the strong perturbation through a turbulent flow. So this, of course, is a sort of a rather academic exercise of essentially extending the Vicsek model for particles in a flow. So all of you know the Vicsek model here in this room, so I won't elaborate on it. Just to tell you that we were not, I mean, we are sort of half crazy, but not completely crazy, in the sense that before us, Nidhi and Nicola Ouellette had looked at a similar problem in a flow which was sort of white in time, stochastic, etc., just to see if you could have flocking behavior. And then Bagalay, around the same time as this paper of ours, sort of looked at this problem for steady vortical flows. So the question we wanted to ask was that if we have model organisms which have which are active, self-propelled, and have Vicsek-like interactions. I now put them in an environment which is noisy. The only noisy environment I can deal with well is a turbulent environment. Luckily, it sort of looks nice if you say that I'm going to model microorganisms in an ocean, so that's one advantage. And we are going to look at what is the role of the size and shape of these guys, all right? I won't go into the details of this calculation. So the strategy is essentially here. So we want to understand what's going on. And this sort of work was done by Amal Rai, Anupam, who was sort of summer students, and Arnob, and earlier Ashok, who was again a summer student of mine. Very wisely, he went on to do a PhD in gravitational wave physics after this work, and Divya, who was also with us. Right, so these are the two. So essentially, how do I model such particles? So again, as I said, applications, I'm skipping mainly the theory. So this has a longer history than what we talked about. So this goes back to the work of Jeffrey, who showed that if you have either disks or rod-like particles and you have their orientation vector P, you can write down the rotational dynamics in terms of alpha, which is their aspect ratio, so it's a shape factor, and the ambient sort of fluid, which you can sort of write in the, so that's the straining matrix and the vortical matrix, but you actually have the dynamics of its rotation. So you can actually know at any given time if it's in a flow where the P vector will point. Then you can write down the translational dynamics. Now this is a little more involved than what we had for spherical particles, because remember, these particles now have an internal degree of freedom because of their shape. So depending on where they're pointing, the effective drag will be different. So I can't plug in a number there, but every, along its trajectory at every time, I need to calculate the effective drag through its mobility tensor and the drag tensor. So I need to know its orientation at all times. So beyond this, what we did, hopefully correctly, was to impose a swimming speed pointing along its orientation vector. That's my activity. I mean, I don't know how to do a more serious job of it, let's say. And then at discrete time intervals, I calculate the average orientation within a radius of interaction, and I reorient myself, all right? So the question becomes, do I always orient? All right? So the caveat, of course, is again, the usual caveat is the dilute suspension, etc. And the fluid field that you again see here comes from the Navier-Stokes equation. That's the party line, essentially. Every time you see the carrier fluid, it's going to be turbulent. Okay, so are these models valid? Again, I'll show you through pictures. So for passive problems, rods and disks, in recent times between experiments and theory, and this is one of our earlier work a couple of years ago, we know that this, I mean, if you ignore the activity part, just the rotational and translational dynamics are absolutely valid to speak about, for example, micron-sized objects in a turbulent flow. What was very nice was, and this we discovered after we put up our paper, was that Pujara and collaborators actually used the same equations as ours to show that the velocity of small microorganisms that they had in fish tanks, or where they were able to trace their trajectory, they didn't look at the collective motion, but they showed that these equations up to again here sort of give rise to absolutely the same velocity field that these ellipsoidal microswimmers have. So these are certain classes of planktons that they have. So our contribution, luckily we did a little more than that, so we are still safe, was to introduce this Vicsek ordering. So essentially the parameters in the problem are many, the radius of interaction, spring velocity, shape, inertia, etc., which drove the poor summer student to ground. And he did simulations with varying all these parameters, which led to 738 different simulations. I'll just show you two results from there. Urna, you're getting worried when I said that number. So essentially here is the take-home message. Well, do they flock or not? So the upper panel are for disks. You start with these swimming particles. You see on the left, there is some evidence. If you're a collaborator in this project, you find that evidence very clear. If not, it will take some convincing. that these sort of disks seem to show a collective behavior. They either this or this, these rods or this, they seem to follow like a herd. So the difference between, let's say, this and this is they are disks of different aspect ratio. This is more disk-like than this. And the radius of interaction is different. The inertia is different. So you have settings where they don't flock, for example, here, where they all go randomly. And you have settings, for example, here and here, where they show very nice collective behavior. So I'll sort of tell you that you can sort of quantify this, and we calculated the nematic order parameters as well as the global order parameters. So I'll just show you the global order parameter and stop, where you can, so the y-axis is the aspect ratio. So here you're really disk-like, here you're really rod-like. The x-axis is the level of inertia, Stokes, it's a log-log plot. And these different plots are for different levels of activity. So what we saw was, however active we made our particles, if they were really disk-like or with very little inertia, there was no way that they were flocking. Green is perfectly ordered. The ordering is close to 1. This is global order. We calculated local order as well. And again, the reason is the following, which it's best I explain. Even if they're swimming, and even if they have these interactions, they cannot overcome preferential concentration easily. So even if you have a dilute suspension, for a given radius of interaction, if the inertia and the shape of the particles are optimal, most of them are pushed into, are forced to be close by, and hence they can orient easily. So, the sort of claim is that fluid mechanics here sort of really pushes you or aids these guys to actually orient. If there was no preferential concentration, which is what we began with, then none of this flocking would happen. That's because for the same number of particles, they would all be far away from each other. However large my radius of interaction would be, there wouldn't be enough of them within that radius to actually orient and slowly start flocking. This, of course, it was, and earlier we had also seen this in two-dimensional flows. So I think I'll stop there without sort of trying to discuss the difference between 2D and 3D and sort of put this up as a conclusion. So thank you once again for your attention and for braving out Turbulence talk. Thanks.
So thank you. So I have two questions maybe. First of all, did I understand correctly? You mentioned that, but I wasn't sure, that this is restricted, the starting model, to small speeds for the particles, sufficiently small speeds. Is that correct, or can I think of very large speeds as well?
You can, because if the inertia is large, then you can have, then the decoupling from the flow is pretty strong. So you can have large speeds. What is critical is that these are small-sized particles, that they're smaller than the Kolmogorov scale of the flow.
But I can imagine that if I am at very large speed, then my time scale is much, I see a kind of static environment. I do not see the time dependence in my turbulent flow.
This is exactly what happens when I was discussing the gravitational settling problem. If your tau p is really large, so tau pg is large, and they fall, to actually understand how they settle, there they do not see the correlation scales in the turbulent flow. So you can get away with uncorrelated slices of the field.
And what is then known, if you can scan all of this regime, what is then known about the velocity distribution? Is it Maxwellian, or is there long fat tails, or what is known?
So the distribution of the individual velocities are so boring Gaussian, etc. What's interesting is
Maxwellian.
Yes, is the relative velocity. So if you have two guys who are coming close to each other, what's the distribution of their relative velocities? And those have fat tails, and the functional form of those tails are dependent on the Stokes number.
So what does it mean, fat tails?
So they have
power law? Or stretched exponentials?
Stretched exponentials. And there they have, and the sort of argument in that stretched exponential is Stokes dependent. Okay. So this is when you're looking at, let's say, the condition relative velocity. So you decide how close you want them to be.
And then my
extrapolate to
second
the-
question
yes.
is, I mean, if you do simulations, probably, at least I would not try to solve Navier-Stokes equation. I would make force fields which look a bit random, maybe add a bit of noise. You know, I would cheat. Is that, do you also do that?
No, we don't cheat.
No. Why don't you cheat?
Why don't
I
we
mean,
cheat?
I would
Good
imagine that it
question.
doesn't matter really, no?
Good question. The point is, if you deal with just Gaussian fields or fields which are solutions of some Einstein-Uhlenbeck process, any of these cheats, then experiments or observations that you have in real turbulent flows, they never agree. And so that cheating is, I mean, that's part
But
of the real problem.
I can make random fields with vortices moving on different scales. I can do all that, but still it will not
Well,
work.
if you can really construct a field which mimics the solution of the Navier-Stokes, as far as I know,
It will not be Einstein-Uhlenbeck, but I will add
something more, yeah. But as far as I know, that
I will
has not
add
been done.
non-conservative forces and all that.
I agree, but as far as I know, that has not been done. I mean, that would be one solution to the
It
Navier-Stokes
would be
problem.
much
But
simpler.
simpler, but then it will not give you, if your end game is to actually try to look at observational. For example, the settling velocity that we were etching there, right? So if you play it with, and people have played with some sort of synthetic fields, you'll never get the distribution that you actually see in observations.
Really?
Yeah. So the sort of fluctuations, the problem is that the fluctuations in just the turbulence is something that has escaped modeling, right?
Yeah, well, but you
Or
could
any
say
closure models.
in the first instance, it's like a chaotic random field, which
Of
is
course.
sufficient.
So the early work in the mid 2000s on this, just on the problem of inertial particle in turbulence, just to show preferential concentration, all of that you can get from what you're sort of saying, synthetic model fields. But then if you're sort of trying to address questions which are more connected to what you actually see in a real turbulent flows, either in experiments or in observations, then you see that those synthetic flows will not get you beyond
Okay,
a point.
I would
which
like to see, because not all turbulence is Navier-Stokes, right? I mean, there are.
Sure. Sorry. What do
I
you
mean,
mean?
there are. I mean, if you look at solar plasmas, it's not Navier-Stokes.
Sure. I mean, for those, the equations will have to change. For example, if you look at the solar wind data, there the Hall terms become very important. And but there, to model that is not easy.
I know.
Yeah. So there is a good physics reason why we have to solve.
I mean, there is a
Navier-Stokes.
good physics reason not to concentrate on Navier-Stokes, because turbulence and what you see
Of
is
course.
probably not related intrinsically to Navier-Stokes, but more to multiple time scales, a kind of random chaoticity in your field. That is probably more important, I would say. But you say no.
I would say no. For example, if I want to understand growth of aggregates in a cloud, let's say, could I get away with not solving the Navier-Stokes for the
And you
flow
say
field?
no. You say no.
And I say no.
Okay, let's see.